My lecture is given below. First of all, I will give some introduction of complex number, then the definition of complex number, operations on complex numbers as ordered pairs of real numbers, properties of fundamental operations on complex numbers, modulus of complex numbers, a special subset of C. C is the set of complex numbers, then Cartesian plane, geometrical representation of complex numbers. The history of mathematics showed that man has been developing and enlarging the concept of numbers. In the remote past, they started with the set of counting numbers and invented by stages to categorize more types of sets of numbers like set of integers, set of positive integers, set of negative integers, set of even numbers, set of odd numbers, set of whole numbers, set of natural numbers, set of rational numbers and set of irrational numbers, and etc. The above mentioned sets are all subsets of the main sets, which is the set of real numbers. Initially, the set of real number and the real number system has been defined, and later all its related subsets have discussed. In my last class, I have discussed in detail about the number system, real line, real set, and all the subset of the real number set. But there is another category of numbers which is not fall in any of the above mentioned category of numbers. Such type of numbers were introduced when mathematicians tried to find out the solution of the following type of equation. Now, this is one of the equation, and in order to solve this equation, we have to find out the value of x, because x is the unknown, x is the variable, and we have to determine the value of x which will satisfy this equation. For this purpose, we can take this plus 1 on the other side of the equation, then we can write x square is equals to minus 1. When we take the square root of both sides of this equation, then one can obtain x is equals to plus minus under root minus 1. We can obtain two values of x. Both values are going to satisfy the above equation. So both values are the solution of this equation. But this under root minus 1 is a suspicious number because it's not a real number. It's not belongs to any of the above mentioned category which are subsets of the real numbers. It's not a real number. It's not belongs to any subset of the real number. And the solution of the above equation is under root minus 1 and which does not belong to any set which is a subset of the real numbers as mentioned above. So, under root minus 1 is not a real number. So, it must be some imaginary number. Therefore, mathematicians invented a new set of numbers which contains imaginary number and labeled this type of imaginary number with iota, I. Such type of numbers are called complex number. A number which contains such type of imaginary number is known as complex number, and the set contains complex numbers is called the set of the complex number and labeled as capital C. A set must be labeled by some capital letters, and the set of complex number is labeled by capital C. Now, what is the complex number? The complex number is a number which can be expressed in the form z is equals to x plus iota y. This is a complex number which is usually labeled by small z. This is the general formulation of a complex number, real number plus imaginary number plus real number, where x and y are real numbers and iota which is equals to under root minus 1 is imaginary number. So a complex number is a combination of real and imaginary numbers, and usually it is denoted by a small z. In order to write a complex number, there must be a positive sign lies between x and iota y, and it is a combination of real numbers and imaginary number. Here x is called the real part of a complex number and y is called the imaginary part of a complex number. The number which lies with the iota must be an imaginary part of the complex number. This is the imaginary part where iota I is read as iota. This is the example. Here are two examples: 3 plus 4 iota, 2 minus 5 by 7 iota are complex numbers. In first example, 3 plus 4 iota, 3 and 4 are real numbers. Iota is imaginary number, and a real part of this complex number is 3 and the imaginary part of this complex number is 4. And in this complex number, 2 and minus 5 by 7 are both real numbers, while iota is imaginary number. Real part of this complex number, when we compare this complex number with this general formulation, real part of this complex number is 2, while the imaginary part of this complex number is minus 5 by 7, because if we have to take plus in between, so the imaginary part will be minus 5 by 7. And here 3 and 4 are integer, while 2 is integer, but 5 by 7 is a rational number but a real number. So the combination of the real number and imaginary number is a complex number. Power of iota. We have idea about the value of iota, which is equals to under root minus 1. But if we take some more integer power of iota, like iota square, iota cube, iota 4, iota 5, iota 10, or iota 100, or iota 1000. So how we can simplify such types of powers of iota? If we write iota square, then we can write iota square means iota multiplies with iota, and the value of iota is minus 1. So under root minus 1 multiplies with under root minus 1. And when we take the square of under root minus 1, then whole square will be cancelled out with this square root sign. So one can obtain the value is minus 1. So the value of iota square is minus 1. If we want to take the value of iota cube, this value can be written as iota square dot iota. Iota square value is minus 1, so we can replace this value over here. Dot iota will be same. So one can simplify it as minus 1 when multiplies with iota will be minus iota. So iota square is minus 1, iota cube is minus iota. And what is iota 4? We can write iota 4 as iota square dot iota square. Iota square multiplies with iota square. And the value of iota square we know, which is minus 1. So minus 1 multiplies with minus 1 will provide us 1. And so on. We can take the value of iota 5. Iota 5. Iota 5 value will be iota, because iota 5 means iota 4 dot iota. Bases are same, power will be add. Bases are same, power will be add, then cube. Bases is iota, power is 1, 1, add is 2. Bases iota, power is 2 plus 1, which is 3. Iota 5 means iota 4 dot iota. Iota 4 is 1, answer of iota 5 will be iota, when 1 multiplies with iota, and so on. Thus, any power of iota must be equal to 1 iota, minus 1, or minus iota, not more than these 4 values. Any power of iota or any larger value power of iota must belongs to these 4 values only. Operations on complex numbers. Following are some properties of complex numbers involving addition, subtraction, multiplication of complex numbers. Here A, B, C, D and K are real numbers. These are some properties of complex number. When two complex numbers are same, means the real part is same as real part and the imaginary part is same as imaginary part. Here A plus B iota and C plus D iota are two complex numbers. A, B, C, D are real numbers. So if two complex numbers are same, it means their real part are same and their imaginary parts are same, or vice versa. You can write if real part of a complex number and imaginary part of the parts of the complex numbers are same, then the both complex numbers are same. It's a vice versa property. And the second property is if we want to add two complex numbers, it means the real part will be added in the real part and the imaginary part will be added in the imaginary part. Its real part is A, its real part is C. So A must be added in C and B must be added in D, the new complex number will be obtained as its real part is A plus C and the imaginary part of the new complex number will be B plus D. Scalar multiplication of a complex number. Here K is a scalar which is a real number and scalar is going to multiply with a complex number. Then scalar multiplication of a complex number means scalar will be multiplied with its real number, scalar will be multiplied its complex real number, its real part, and scalar will be multiplied its imaginary part. So it means the new complex number which is obtained will be its real part is Ka and its imaginary part will be Kb, which is a scalar multiplication of its real part, original real part by K and the imaginary part by K. When we subtract two complex numbers, it means we are going to subtract its real part from the second complex number's real part from the first complex number's real part. So that real part must be subtracted from the real part and imaginary part must be subtracted from the imaginary part. You can open this minus sign and you can multiply this minus sign with these two plus signs. So one can simplify, we can obtain this equation. This is a new complex number. Its real part will be A minus C and imaginary part will be B minus D. Real part is going to subtract from the real part and imaginary part is going to subtract from the imaginary part. So one can obtain a new complex number by subtraction of two complex numbers. Similarly, we can multiply two complex numbers. You can multiply these two ordered pairs in a simple manner. Initially, A will be multiplied with the whole quantity C plus B iota, then plus sign, and B iota will be multiplied the whole quantity C plus D iota. One can obtain this expression when A multiplied with this quantity, we can obtain AC plus AD iota plus when this term will be multiplied with this quantity, then we can obtain BC iota minus, because iota square. Iota square is minus 1, this is minus 1 and B and D, BD minus BD one can obtain. When we simplify or we will write in simplified form, so we can write it as, we can combine the real parts and we can separate the imaginary parts. So here real part is AC and BD. These are two real numbers, while this AD iota, BC iota are two complex numbers. So we separate the real numbers and the imaginary numbers. So from here we can take common iota and we can obtain the following form: AC minus BD plus AD plus BC. This is a new complex number which we have obtained from the multiplication of these two numbers, and it's the real part of this complex number is AC minus BD and the imaginary part of this complex number is AD plus BC. Conjugate of complex numbers. Complex number of the form A plus B iota and A minus B iota which have the same real parts and whose imaginary parts differ in sign only are called complex conjugate of each other. These are two complex numbers. These are same, but only the difference in between their signs. Their real parts are same, their imaginary parts are same, but the signs are different. And then these two complex numbers are called complex conjugate of each other. This is the concept of complex conjugate. So there are three examples of complex conjugate here. 5 plus 4 iota and 5 minus 4 iota are two complex conjugate of each other. 5 plus 4 iota is the complex conjugate of 5 minus 4 iota. 5 minus 4 iota is the complex conjugate of 5 plus 4 iota. The concept of the complex conjugate lies in the complex number system. If there is a complex number, if there is an imaginary number, then there lies a concept of complex conjugate. So, the conjugate of 5 plus 4 iota is 5 minus 4 iota. And vice versa is also true. The conjugate of -2 plus 3 iota is -2 minus 3 iota. And we can see here that in order to find the complex conjugate of a complex number, we have to change only the sign of the imaginary part. Only. We will not change the sign of the real part. Here the real part is 5, and in the complex conjugate the real part is 5. Here the imaginary part is 4, and here the sign of the imaginary part is negative and the imaginary part is -4. Similarly, the real part is -2 and the real part is -2, but the imaginary part is 3 and here the imaginary part is -3, and we have to change the sign of the imaginary part in order to get the complex conjugate of another complex number. The conjugate of the -5 iota. This is a complex number whose real part is 0, but this is a complex number, so its complex conjugate is 5 iota. We have to change only the sign of the imaginary part. Complex numbers as ordered pairs of real numbers. We can also define a complex number in the form of the ordered pair AB. Both complex numbers are same, but their representation is different. This is written in the form of iota, but this complex number which is same as this, but this complex number is written in terms of the ordered pair. Let C be the set of the ordered pairs, because C is the set of the complex number, and ordered pair can be written as the complex numbers, or complex number can be written in terms of the ordered pair. So the ordered pairs belong to the set of the complex numbers. Let C be the set of ordered pairs belonging to R cross R, because R cross R is the Cartesian product of two sets of the real numbers, and the Cartesian product, the set of the Cartesian product contains the elements which are of the form of the ordered pair. So AB is basically belongs to the set of the Cartesian product of R cross R, because A belongs to set of R and B belongs to set of R, and when we take the Cartesian product of R cross R, then Cartesian product element must be same as A cross B, and so A cross B, AB belongs to the set of the Cartesian product R cross R, which are subject to the following properties. These two are complex numbers. We have already discussed such type of properties of complex number in terms of iota as earlier, and here we write the same properties in terms of the ordered pair. So two complex numbers must be same if their real parts are same and imaginary parts are same. Two complex numbers we can add, and we can obtain a new complex numbers with a new combination. The new complex number we can obtain with the addition of the real parts and with the addition of the imaginary parts. Real part will be added real part, imaginary part will be added imaginary part. And we can take scalar multiplication of a complex number as well. If k is any real number, then we can multiply this scalar with a complex number, and one can obtain a new complex number and whose real part is Ka and whose imaginary part is Kb. K is a scalar multiple of old real and imaginary part. We can multiply two complex numbers and one can obtain a new complex number, as we proved earlier in the previous slides. And it's the new number which we can obtain from the multiplication have real part is AC minus BD and the imaginary part is AD plus BC. You can find out by itself here. We can add subtract two complex numbers. Real part must be subtract from the real part, imaginary part must be subtract from the imaginary part. So these are the properties same as defined earlier, but in form of the ordered pair, because we can write a complex number in terms of the ordered pair. For example, we have to find the sum, difference and product of two complex numbers. 8, 9 and 5 minus 6 are two complex numbers, and we have to take the sum, difference and product of the complex number. These two complex numbers are in the form of the ordered pair. And in order to take the sum, we can write these two complex numbers like here, and real part must be added in a real part, like 8 plus 5, comma, and 9 plus minus 6. 9 plus minus will be minus, so 9 minus 6, when we add 8 plus 5 is 13, 9 minus 6 is 3. Comma is the standard form of the ordered pair, and so this is a new complex number 13, 3, which we have obtained from the sum of the two complex numbers. And there is a difference of two complex numbers, 8, 9 and 5 minus 6. The real part must be subtracted from the real part, and the imaginary part must be subtracted from the imaginary part. When we take minus will be plus, so it will be 9 plus 6, which is 15, and 8 minus 5 is 3. Product 8, 9, 5 minus 6. And we have to take product of these two complex numbers by using the formula. This is A, this is B, this is C, and this is D. And the formula is in the previous slide, which is AC minus BD, AD plus BC. So we can put the values of A, C, B, D in the previous formula, and one can obtain this expression 40 plus 54, 45 minus 48. When we simplify, we can obtain 94 minus 3. 94 is the real part of the new complex number, and minus 3 is the imaginary part of the new complex number. Imaginary part can be positive, negative. Real part can be positive, negative, but it should be real numbers. So this is a real number. This is a real number. Here are three complex numbers, real and imaginary parts, and are three are real numbers. So, set of complex numbers satisfies all the field axioms, and these axioms are given below. The additive identity in the set of complex number is 0, 0. 0, 0 is a complex number. If we talk about the set of the real number, the additive identity in the set of real number is only 0. What is the additive identity? We have discussed in detail in our class. Additive identity is a number which we can add in any number. The number will be the same. There will be no change. So 0 is the number which, if we add 0 in A, 0 plus A is equals to A. So, but in case of the complex number, 0, 0 is the additive identity. If we add 0, 0 with some complex number A, comma B, then the answer must be AB. So 0, 0 is the additive identity in case of the complex numbers, and we cannot write only 0 is the additive identity for a complex number. Every complex number has the additive inverse. Minus A, comma minus B, that is, if AB is a complex number, any complex number, the additive inverse is the number. If we add the additive inverse with the original complex number, then we will obtain the additive identity. So, if AB is the complex number, then additive inverse is minus A minus B. If minus A minus B is the complex number, then AB is the additive inverse. So, additive inverse of a complex number must belongs to the set of the complex numbers. The multiplicative identity is 1, 0. That is, if AB is a complex number and we multiply this complex number, which is 1, 0, which is multiplicative identity as well. If we multiply this complex number with any of the complex number, we can obtain the same complex number. So 1, 0 is the multiplicative identity. Similarly, in case of the real numbers, we write multiplicative identity is 1. But when we write the multiplicative identity in the case of the set of the complex number, it must be 1, 0. And so, every non-zero complex number has multiplicative inverse. The multiplicative inverse of AB is A over A square plus B square minus B over A square plus B square. This complex number is a number and is a multiplicative inverse of this complex number, because when we multiply these two numbers, these two complex numbers, we will obtain the multiplicative identity. So, This is the multiplicative inverse in case of the complex number. If we talk about the multiplicative inverse in a set of the real number, then the multiplicative inverse of 2 is 1 by 2 and the multiplicative inverse of the 1 by 2 is 2. Because when we multiply these two numbers 1 by 2 and 2, we will obtain the multiplicative identity which is 1. But in this case, we can generalize the multiplicative identity by writing the complex number in this form. Complex number also holds the distributive property, and here are three complex number, and we can write this complex number by multiplication with this complex number plus sign as it is, and this complex number will be multiplied this complex number. So distributive properties hold in terms of the complex numbers as well. Properties of fundamental operations on complex numbers. Here is the example. Find the multiplicative inverse of this complex number. -47 is the complex number, and this is the formula in order to calculate the multiplicative inverse of this complex number. We will write the value of A, which is -4, value of B, which is 7 in this formula, and one can obtain Z inverse, which is this. When you multiply these two complex numbers, -47 -4 divided by 65, -7 divided by 65, and when you multiply these two complex numbers, you will obtain the multiplicative identity. And the calculations are simple. Just put the values of A and B in the formula, you can obtain this number. Properties of fundamental operations on complex numbers. Now, the set of complex numbers does not satisfy the order axioms. Thus, we cannot say that one complex number is greater or lesser from the other complex number. That is, if 1 plus iota and 1 minus iota are two complex numbers, we cannot decide which one is greater or which one is lesser than other. As we can decide in the set of the real numbers, we can write 2 is greater than -2, -2 is lesser than 2, 2 is equals to 2. We can write over here the 1 plus iota is equals to 1 plus iota, but we cannot say that 1 plus iota is greater than or lesser than 1 minus iota. We cannot compare any two complex numbers, which one is greater or which one is lesser. But in the real number system, on the real line, which is easily depict that which real number is greater and which real number is lesser. So, order properties are not hold in terms of the complex numbers. Modulus of complex number is the distance from the origin to the point representing by the complex number in the complex plane. Complex numbers are plotted in the complex plane, and complex plane is also known as Cartesian plane because complex number is the Cartesian product of R cross R. So, we can plot a complex number in a Cartesian plane, as we can identify the real number on the real line. So, we can identify a complex number in the complex plane, which we discuss later in our slides. The modulus of complex number is generally denoted by x plus iota y absolute modulus. This value will provide us the absolute value, positive value, because it provides us distance. Distance cannot be negative, and it's the symbols we use to calculate the distance. The symbol we use to calculate the modulus is these two lines. We write the complex number z between these two lines. It means the distance of that point in the complex plane from the origin. So, modulus or distance is the same thing. Mod always provide us a distance, always provide us a positive value. For convenience, we can denote a complex number by z. If z is equals to x plus iota y, then mod z is equals to under root x square plus y square. This is the distance formula. This is the distance formula between a complex number and the origin. We can write the distance between complex number and origin in this form. under root x square plus y square. Example, find the modulus of the complex number 3 plus 4 iota. We have to compare this complex number with this complex number. Here x is 3, y is 4. Similarly, as for this complex number, we can write the absolute value of this complex number like this. Here x is the real part, y is the imaginary part, and here we can put the value of x, which is 3, y, which is 4 in the formula, and one can obtain the modulus of the complex number, which is the distance of this complex number from the origin, which is 5. A special subset of C. A special subset of C is the set of real numbers. A0. A0 is a real number and A0 is a complex number as well. We consider a subset which is a special subset of C whose elements are of the form A0. This special subset is the set of the real number. Set of the real number is a subset of the set of complex number, because every real number is a complex number, but every complex number is not a real number. So complex number set is more generalized than the set of the real number. This is a complex number and this is a real number. This is a special kind of a complex number whose imaginary part must be 0, and it's a subset of complex number set. It is a special subset of the set of the complex numbers, and it's a real number as well, because when we write this number, we can write a plus 0 iota. When 0 multiply with iota, it will be 0. Ultimate answer is A0 is equals to A. So it's a special kind of a complex number, and is a whose always imaginary part must be 0, and is a real number as well. Let A0, C0 be two elements of this subsets, these two elements of this special subset, and of special subset of the complex number set. Because it's the subset of the complex number set, so we have to use such type of notation in order to define the complex number. And then we can add these two complex numbers. The real part must be added in real part is again a real number in here, because the imaginary part is 0. Yes, when we add these two numbers, complex number, we will obtain a new complex number, which is a real number as well. Similarly, we can multiply with a scalar any number of this subset. We will obtain a new complex number. Similarly, we can multiply these two complex numbers. One can obtain again such type of number, which is a complex number, which is a real number as well. The multiplicative inverse of any element of this special set is 1 over a is 0, where a is not 0, and because if a will be 0, then it will be undefined, so a cannot be equal to 0. So we can obtain a multiplicative inverse as well, which is also a complex number and also belongs to this special subset. So real number is a special subset of the complex number. We can write every real number in terms of the complex number. Cartesian plane. The Cartesian product of two non-empty sets A and B is denoted by A cross B. The element of A cross B can be expressed as A cross B. This is a general element of this Cartesian product, which we must be written in terms of the form of the ordered pair. The first element of the ordered pair belongs to the first set, while the second element of this pair must belongs to the second set. So here x belongs to the A and y belongs to B. This is the definition of the Cartesian product of two non-empty sets A and B, and labeled by A cross B. And in our topic, we have discussed about the Cartesian product of two sets of the real numbers. The Cartesian product of R cross R, where R is the set of the real numbers, is called the Cartesian plane. We can plot such type of the Cartesian product in a Cartesian plane, because we can plot a set of the real number on a real line. But we talk about the Cartesian product of two real lines, we will obtain a plane. We can plot any number on the real line, and we can plot any of this number in the Cartesian plane. Any xy, ordered pair of xy, we can plot on the Cartesian plane, because any element belongs to this Cartesian product. So any ordered pair belongs to R cross R can be plotted on the Cartesian plane. Such type of plane is also known as real plane, because these two sets are real sets, or coordinate plane as well. If a point P on the coordinate plane corresponds to the ordered pair AB, where A, B are called the coordinates of P, A is called the x coordinate and B is called the y coordinate. So, if we can plot a point in a coordinate plane, and we label that point with P. Due to the coordinate plane, the coordinates of that point will be AB. Then A is called the x coordinate, because A is the distance from origin to that point along x-axis, and B is called the y coordinate, which is the distance of that point from origin along y-axis. Corresponding to every ordered pair which belongs to the Cartesian plane R cross R, there must be only one point in a plane, and corresponding to every point in the plane, there is only one ordered pair in R cross R. So every point in the Cartesian plane must be defined by the ordered pair, or every ordered pair defined in a Cartesian plane must be labeled by some point. So there is a one-to-one correspondence between R cross R and the plane. R cross R and plane is the same thing, because plane is actually a span of R and R. Every point in the plane, every point in R cross R are labeled by the ordered pair, and ordered pair is defined by A cross B or XY. This picture depicts the R cross R Cartesian plane, or you can say a Cartesian plane, or simple a plane. There are two axes, x-axis and y-axis. These two are real line. X-axis line is a real line. Y-axis line is a real line. So this plane shows the every point in this plane is labeled by the ordered pair. Either this point or any other point over here, wherever, is labeled by the ordered pair, and ordered pair belongs to the set of R cross R. So the set of R cross R spans, or set of R cross R provides a plane, and every point of this R cross R set is in the form of the ordered pair, or every point in that plane is in the form of the ordered pair. This is a point 2, 3. Here x and y coordinates both are positive. So it lies in the first quadrant. This plane has 4 quadrants: first, second quadrant, third quadrant and fourth quadrant. In this quadrant, x-axis and y-axis both are positive. In this quadrant, x-axis negative, y-axis positive. In this quadrant, x-axis and y-axis both negative. In this quadrant, x-axis and y-axis, x positive and y negative. So this is the point 2, 3, which lies in the first quadrant, and so we can write labeled as, if we plot a sketch over here, this is a distance from origin to up to 2 along x-axis, which is 2. X coordinate and y coordinate is the distance from origin along y-axis up to 3. So this is 2, 3, and this is the distance 2, 3, and this is the label of the point 2, 3. So we can plot, and this point belongs to the set of the Cartesian product of R cross R.
and we can write this is the Cartesian plane, this is the Cartesian product which spans the total plane, this is the element of this Cartesian product. We can write any point over here. Of that point, the x-axis will be negative and y-axis will be positive, and so on. Geometrical representation of complex numbers. We can represent a complex number by point in the coordinate plane. In this representation, every complex number will be represented by one and only one point in the coordinate plane, and every point of the plane can be expressed as one and only one complex number. It means every point in a plane is a complex number, or any complex number can be represented in a plane, and the plane is also you can say a complex plane. So ordered complex numbers are written in form of the ordered pairs, and ordered pairs will be plotted in the Cartesian plane, or you can write a complex plane. The components of the complex numbers will be the coordinates of the point in the plane. Complex number component means real part or its imaginary part are the coordinates of the ordered pair in that plane. In this representation, the x-axis is called the real axis and the y-axis is called the imaginary axis. So the real part are labeled along the x-axis, and the imaginary part will be labeled along the y-axis. X-axis is real, y-axis is imaginary axis. The coordinate plane itself is called the complex plane or the z-plane. The figure representing one or more complex number on the complex plane is called a Venn diagram. The point on the x-axis represents the real part of the complex number, whereas the point on the y-axis represents the imaginary part of the complex numbers. And this picture depicts the representation of the complex number in a complex plane. The complex number is 3 plus 2 iota, and this is the general number a plus iota b, any number. This is any a is the real number, so it's along the x-axis. B is the imaginary number, so it is along y-axis. A is any distance from 0 to a. It's a general distance a. It's the general distance from 0 to along y-axis, which is b. And 3 plus 2 iota is a specific number. 3 plus 2 iota, 3 is the distance from origin to that point along x-axis, 2 is along y-axis, so this is 3 plus 2 iota. If we minus 4, 3 iota, minus 4 along x-axis, minus 4 is a real part, and minus, it means it will be along x-axis, and this left side of the origin is the negative of x values. So this is the minus 4, this is the positive 3, which is positive 3 is the imaginary part, which is along y-axis. So here is a complex number minus 4 plus 3 iota. And here is the complex number minus 2 minus 3 iota, where real part is negative, where imaginary part is negative, and it's a third quadrant. Here x is the real part, which is minus 2, and this is the point. This is minus 3, this is minus 3. Here x negative, y negative, and this is minus 2 minus 3 iota is the representation of this complex number. Assignment. All questions of exercises 1.2 and 1.3 of 11th textbook, Punjab textbook, Board Lahore, or any question related to this topic from any book. You can ask question. You are free to ask any question about this topic from any book, from anywhere. But this is the simple to understand in such type of situation, in order to understand this topic. So these are the reference books, and thanks. I'm waiting for your questions. And again, you are free to ask any sort of question related to this topic from anywhere. Thank you.